Hello, everybody. Welcome to today's College of Engineering Virtual Brown Bag Series presentation by Dr. Yan Wan, Autonomy and its Smart City Applications. Thanks for joining us today. Just a few housekeeping items before we get started. If you have any questions at the end of the presentation, feel free to send them or put them in the Q&A chat on the side, on the right-hand side. If you go to the top right-hand corner of your screen, you'll see a little box with two little question marks. That's where the Q&A is. Drop your question in there. We'll try to get to it as soon as possible at the end of the presentation. Also in there, you'll see the link to this rest of the schedule for the rest of the semester. We've got some great speakers coming up. We're excited about it. We hope you'll join us for the rest of the events. So without further ado, let's get to it. Dr. Yan Wan is a professor in the Electrical Engineering Department at UTA. Her research interests include the modeling, evaluation, and control of large-scale dynamical networks, cyber-physical systems, stochastic networks, decentralized control, learning control, networking, uncertainty analysis, algebraic graph theory, and their applications to urban aerial mobility, autonomous driving, robot networking, and air traffic management. She has received research grants from the National Science Foundation, Office of Naval Research, Army Research Office, National Institute on Standards and Technology, IEEE, Ford, Toyota, Lockheed Martin, and MITRE Corporation. Her research has led to over 190 publications and successful technology transfer outcomes, and she has earned several prestigious awards, including the NSF Career Award. Dr. Yan, I'll turn it over to you. Dr. Wan, sorry, I'll turn it over to you.
Thank you, Jeremy, for the introduction. It's my pleasure to share with you the autonomy and its smart city applications. So this is the overview of this talk. I'll first give a very brief background on dynamical systems and control because these are important concepts for autonomy. And then I'll briefly introduce the history and trends, the challenges, and also the enabling technologies for autonomy. And next, I'll use some example applications to show how the enabling technologies for autonomy can be used for smart city applications. And I'll talk about some of the applications that my colleagues and I have been working on, including autonomous driving, smart emergency response, and also urban aerial mobility. First, I'll briefly talk about the concept of dynamical systems. So the dynamical system doesn't really mean that the system has time-varying signals. So for instance, here I show a very simple example of a time-varying voltage source and also a resistor. So although the voltage source has time-varying signals, time-varying voltages, the system is not considered as a dynamical system because the voltage across the resistor instantaneously copies the voltage of the voltage source. In contrast, if we add the inductor and also the capacitor to the circuit becomes a dynamical system because the capacitor and the inductor are energy storage devices. And because of the past voltage of the system affects the voltage of the system in the future. So the system becomes dynamic. So basically a dynamic system must have memory to be able to learn the past and become intelligent. So the past information affects the information of the system in the future. So this is very important concept because it allows us to see that the data is not really static for systems of intelligence. So there is a time dependency of the data that is important for the system. So the systems and control field provides systematic approaches to capture such data of the time dependence, such as the state space models. So for example, the state space models are shown on the right. We have the states to capture the past information up to the current time, and also the state allow us to predict the future with the derivative term over there. So the derivative term captures the dependency on time. So next is the concept of automatic control. So built upon the dynamical systems concept, the control, and typically it's a feedback control, uses the output to change the system's input. For example, the red feedback line shows in the picture. So the output feeds back to the input, and the input together with the reference gives the error for the controller to generate the actuation signal. So this actuation signal allows us to shape the dynamics of the system to meet certain performance requirements, for example, rejection to disturbances. And this field allows us to come up with systematic ways to capture the system's performance, for example, stability, steady state error, transient performance such as overshoot, and also robustness measures such as gain and phase margins. So all of these are quantified measures allow us to measure the performance of the system. And also the field also give us systematic approaches to design a wide type of controllers such as P, PI, PID, LQG, and many others. So the control systems are very common in our daily lives, and the most typical example is the air conditioner, and especially in Texas, we badly need it because of the very hot and also cold days as of today. So in air conditioner, we have the sensors and controllers similar to many other control systems. In air conditioner, the sensors are used to monitor the temperature, and also the controller are used to actuate the heating control cooling system, for example, to turn it on and off. The sensing and the control are very important for all of the control systems. And here's another example. So this is the driving scenario. If a human being is driving, the eyes become the sensors, and the controllers are basically the brains that decides whether we want to, for example, press a pedal. If it's cruise control, automatic cruise control, then all of this is done by the computers. The sensors in this setting is a speedometer, and also the controllers are used to actuate the engine to control the speed of the vehicle to meet certain performance requirements, for example, in rejection to disturbances like the hills. The first feedback control system was considered to be the Cornelis Drebbel's oven for incubating chicken eggs. That was in 1620. So as the figure shows on the left, the wells can be opened and closed to have the right amount of air in the system for the fire. So this was a very simple mechanical control that can be also illustrated in this liquid level control. So in this example, the system controls the right level of the height of the liquid, and this is typical even in our toilets, right? So all of us have it in our homes. In this control system, when the water level is low, then the float is open and the water can flow into the tank. And when the water level is high, the pipe is closed and the water cannot go in. So in this very simple system, the float becomes both the sensor to detect the high level of water and also the actuator to turn on and off the water flow. So those were very simple mechanical control. Later on, very sophisticated mathematical control theory have been developed, and the technologies have been applied to, for example, industry automation and also flight control systems. This is a summary of the history and the trend. So initially, there was the mechanical control that was built based upon simple intuitions. And then there was mathematical control theory developed and also allows the control to be applied to sophisticated physical devices. And this is not the end of it. If we look at control theory, they are fundamentally decision-making theories that allow us to come up with optimal decisions. So they can be applied to much broader applications that are not just the physical devices. So this is in alignment with the industry revolution. So we have these 4 industry revolutions. The first one is Industry 1.0, which was considered to be the mechanization and also water stream power. And then in Industry 2.0, it was featured by electrical energy mass production and also the chemical industry. And in Industry 3.0 is something that we are very familiar with that includes the automation, computers, internet, and also electronic devices. This leads to the next step, that is the Industry 4.0, which is featured by autonomy, big data, AI, IoT, cloud computing, robotics, and also cyber-physical systems. So we can see that the transition from automation to autonomy marks the transition of Industry 3.0 to Industry 4.0. So in automation, the machines basically are conducting function-specific tasks defined by human. And also in autonomy, the systems have more intelligence to react on uncertainties, unknowns, and also unexpected events and faults. The picture on the bottom shows a future society in Japan. And you can see that in finance or health or agriculture, these Industry 4.0 technologies will play an important role. So the societal needs lead to the new horizons about the applications and also system requirements. The new applications in smart cities include, for example, precision agriculture, where the unmanned aerial vehicles and also ground vehicles help to monitor the plants and also take care of them. Aeronautics, infrastructure health monitoring, energy smart grids. So smart grids basically utilizes renewable energies to provide the power. And environment, so human and environment are deeply connected, and the relationship really needs to be understood better. The smart health care basically allows us to stay at home and get our disease diagnosis. Smart manufacturing, intelligent transportation, where the autonomous vehicles will become the future. Epidemics control is also very important, as we see from the COVID. So in these new applications, there are new requirements about the systems design and control because of the existence of unknowns, uncertainties, and attacks. So according to the National Science Foundation, the new performance requirements are captured in the follows. First is the more capability of the system to conduct very sophisticated tasks. The second is adaptability to changes of the environment. Third is scalability, especially with systems of increasing sizes, such as the traffic system. So computing capability becomes the issue. The fourth is resiliency to attacks and faults and allow the system to recover to the operation stage in a very short time. Next is safety, especially for autonomous driving. Security is also important. That includes both hardware and software security. And also usability is important for all systems to be able to get used. So to address this kind of new requirements, we have some new enabling technologies that need to be combined with control. The first is cyber-physical systems. So as the picture shows on the right, the cyber-physical system concept is as follows. So it includes the cyber components and also the physical components. The cyber components and the physical components are integrated together. They cannot be separated. The cyber components include computation, communication, and control, and the physical components include the system dynamics, the environment, and the physical devices. So the other component important is the networking. So basically allows this system to be connected to the internet and also each other. So this is basically the IoT type of concept. The second technology is AI and machine learning and other data-driven approaches. One important machine learning branch is called the reinforcement learning, which combines with the feedback controls concept. So reinforcement learning really sits between the optimal control and adaptive control and allows the environment to be learned to make forward in time decisions. So right now, people are very interested in interpretable machine learning, right? Reinforcement learning is very promising that allows the learning to be interpreted because of the controls theory as a basis of it. The next technology is the stochastic systems and uncertainty quantification that allows the agents to have the intelligence to address uncertainties. Next is multi-agent systems, and in particular graphical games that allows agents to have the self-interest. Next one is the networks, complex systems, and also large-scale systems theory that allow us to come up with effective computation with reduced order analysis. So next, I'm going to talk about some smart city application that shows how the technologies I mentioned in the previous slides can be used for the agents to be equipped with more intelligence. And the first one is autonomous driving, and I'm going to show how the game theory and also reinforcement learning are being used. So this is with my colleague, Dr. Frank Lewis, and also our colleagues at Ford Company, and also some of our students. So in autonomous driving, the agents need to come up with decisions that are safe and also efficient. So here are two illustrations about the solutions that we made. So for example, the right picture here shows the intersection crossing where the blue vehicle comes to the intersection first. So according to traffic rules, the blue vehicle really has the right of way, so it should cross first. However, something happens unexpected. The green vehicle is very aggressive and it goes to the section and it does not stop and want to ride over the blue vehicle. So the blue vehicle needs to have the intelligence to follow not only the traffic rules, but also address these unexpected events like the green vehicle. So in this case, we see that the blue vehicle tries to cross intersection first, and when it sees the aggressive green vehicle, it stops and to let the green vehicle pass first to ensure safety. The picture on the right shows a similar scenario. The blue vehicle tries to cross the lane, but it noticed that the red vehicle goes at a very high speed, so it changes its decision and maintains at its original lane to ensure safety. So to have the autonomous vehicles with such intelligence, we need to have the games theory approach to let the autonomous vehicles can evaluate their own performance costs and also address unknown scenarios, unknown actions by the other vehicles. So we spent a lot of efforts in developing the game theory and also the reinforcement learning to have the autonomous agents with such intelligence. And funded by some of our other grants, we look at the graphical games and also distributed reinforcement learning. So here's a brief background. So in control, multi-agent control, the consensus has been studied a lot, but the consensus does not generally produce optimal decisions. And distributed optimal control has also been studied, but it does not allow the agents to have self-interest. So the game theory is a useful mathematical framework because it allows agents to have the self-performance cost to be optimized. So the game is not new. The standard game is not a new concept, right? So it has been there for a long time, but the standard games use static and immediate cost, so they're not dynamic. But in differential multi-agent games, the game theory is integrated with the dynamics and also the control theory to come up with feedback optimal solutions. And in scenarios where the agents cannot have all the information of the systems because of the limited sensing capabilities, we need to come up with the graphical game. So basically we use graph to capture the limited communication capabilities. And we have developed results for games with incomplete information to address unknowns, stochastic games to address uncertainties, and also new games with distributed Nash solutions. And here are very brief illustration of the results. So this is the standard graphical game setup. I'm not going to go deep into the math, but fundamentally you see each agent has a cost function, its own cost function to optimize. And reinforcement learning can be used to come up with optimal solutions. And the agents rely on the communication graph to talk to only their neighbors. So in many scenarios, the agents cannot have the complete information. So consider a group of UAVs in the air, the unmanned aerial vehicles in the air, and they want to have collision avoidance. So a vehicle may not know the other vehicle's type. For example, is it a jet or something else? And it does not know their action, possible actions. So in that sense, the agents are playing a game of incomplete information. So what we do is to come up with Bayesian graphical games, which allows the agents to learn the type of the game. So this is done through a belief update procedure. So the actor-critic framework is typical for reinforcement learning to come up with a decision, but we add a belief update allows the agents to have the intelligence and learn the type of the game that they are playing. So the other direction we worked on is the stochastic games under uncertainties. The uncertainties can come from multiple sources, for example, the environment. And this pictures here show how the wind field, which is uncertain, can affect the system's performance. And the uncertainties can also come from the agents themselves. So for instance, as a human, right, we make random decisions all the time. Like today, I may eat apple, and tomorrow I may eat pear. And there's really not a justification on what decision that I make. So in the future, the intelligent agents are going to have such random decisions as well, and we use uncertain intentions to capture those. So to develop the game solutions that can deal with this kind of uncertainties, we come up with the stochastic games. So in stochastic games, the performance cost that each agent tries to optimize has this expectation term in it. So the expectation term allows the agent to evaluate across a range of uncertainties and come up with the best decision. However, evaluating this expectation operation can be time consuming, and we come up with a scalable uncertainty evaluation method called MPCM-OFD. So the brief idea of it is shown here. So basically, it uses it smartly chooses a few samples to come up with the best decision. So this allows the order of computation to be reduced and breaks the curse of dimensionality for decision making. So this shows how the agents can address the uncertainties. And we also come up with games that can come up with both optimal and also distributed solutions limited by the graph topologies. And we found that the existing solutions, game solutions, either is optimal or is distributed, and we come up with a new game setting with extra terms that allows the equation to be decoupled and come up with decisions that are both optimal and also distributed. So that was the application 1 on autonomous driving, shows how the game theory and also reinforcement learning can be used for the agents to deal with uncertainties and unknowns. And the second application that I'm going to talk about is a smart emergency response using UAVs. So in 2013 to 2017, we formed a group called the Smart Emergency Response System with collaborators from Boeing, MassWorks, National Institutes, MIT Lincoln Lab, and some other universities. So this effort was to attend the Smart America Challenge initiated by the White House. And we come up with a smart emergency response system of both air and ground vehicles to assist with emergency response. And the technology was appraised by the chief technology officer of the time as an exemplary success. We also participated in the FRL Swarm and Search AI Challenge. And the purpose here, as the video shows, is to have multiple UAVs search the mountain area and find the fires and predict the dynamics of the fires. And it's a complicated scenario because we don't know where the fires are, we don't know the wind conditions, and also the elevation of the mountain changes very largely. So we come up with coordinated solutions to address all of these different tasks, and we got the first place in one competition run. So another emergency response direction we worked on is on-demand emergency communication. So in emergencies, the communication is very, very important. And it was studied in Hurricane Katrina that the complete devastation of the communication infrastructure is a key feature, is a key reason that lead to the delay of the emergency response. So to address the issue, there are various on-demand emergency communication technologies that are being used, including, for example, the cells on wheels, which are trucks that are carrying the communication devices, the amateur radios, and also the helicopters, but they all have their limitations. So to address this, we consider using UAVs to deliver the on-demand communication, and this cartoon shows the idea. So in an emergency, the cellular towers may be down, and what we can do is to send out the UAVs to the disaster area. And the UAVs set up the communication network in the air and provide the Wi-Fi service to the ground to facilitate the emergency response. And the features of the system include, for example, the communication infrastructure is independent of any of the ground facilities, and they can be quickly deployed, flexibly configured to emergency needs, and also provide long-range and broadband communication. They should be simple to operate and also cost-effective. So to address this, we come up with a solution that allows the UAVs to be equipped with directional antennas. The directional antennas allows the energy of communication to be focused on certain directions to reduce the energy and also reduce the disturbances. So this requires the antennas to be self-aligned despite the disturbances and also the mobilities of the UAVs. To have such intelligence, we need the cyber-physical systems concept. So this picture here shows the tightly integrated cyber and physical components. So basically, the communication facilitates the control, and on the other direction, the control facilitates communication. So this one shows our very early prototype that shows, despite the movement of the UAVs, the antenna still faces a certain direction, and we don't need the humans' interference to it. So the CPS concept is described by the following two directions. One direction is a control that benefits the networking. So basically, we have intelligent control of the direction antennas that allows the communication channel to be formed despite of the disturbances. And on the other direction, in, for example, unknown environment, the GPS is not known, right? And in this setting, we can have the communication signal, which is a received signal strength indicator, to be additional measurement signals for the control. And the two directions allow us to come up with a robust communication channel despite of various disturbances. And this is the solution of our software. So the complete framework has the UAV's intention, stochastic intention estimation, and also the reinforcement learning-based optimal control to come up with the decision even when the communication environment is unknown. So the reinforcement learning will be able to learn the uncertain communication environment. We come up with the software and hardware for the system. So this is a drone platform, and we have the directional antennas control on it. We also developed the computing device that allows the that is very small size and also low weight that can be put on UAVs. So extension, this is the extension of the communication system that we built. So we come up with a networked computing system that can also do distributed computing among the UAVs and also other robotic platforms. And the solution includes 4 parts. One is the quadrature, the UAV platform, the control unit, the communication unit, and also the computing unit, which utilize some virtualization functions. As you can see, this shows the cyber-physical systems concept that integrates all of the different things. Supported by the National Science Foundation CRI grant, we built this networked computing system to support the community. So all of our the solutions are listed in this website, and also we conducted many workshops to promote this area, and also we organized several student design competitions for this for research groups to use this platform. So there's the upcoming one in May this year. So here are a couple of disaster drills that shows our solution. So the first one was conducted in 2014 in Austin Fire Department, where we show the UAVs, the unmanned aerial vehicles, and also the ground vehicles together can quickly find the victim in a chemical leaking environment. So we don't know where the victim is, and the environment is complicated. But we can send out the UAVs. The UAVs have the aerial view that can easily detect the victim and send such information to the robot controller. The UAVs also establish the aerial communications that allows the robot operator to be able to remotely control the robot. So the coordination among the UAVs and also the ground vehicle allows the system to quickly find the victim. So the second video on the bottom here shows the use of the UAVs to provide on-demand emergency communication. So in this scenario, this is conducted with Denton Fire Department. This was a full disaster drill where the Red Cross and also police officers, the hospitals are involved. So in a post-tornado scenario, we don't know the victims. So in the first few minutes of the disaster, we send out the UAVs, which can find the victims where they are and send such information to the management center. And the management center is located inside a room. The emergency people do not need to leave the room and directly get the information from the disaster zone. So such information is very critical because they can be handled as the first few minutes of a disaster. So this video, as upper right, is from the Canada Discovery Channel that shows the use of UAVs in multiple scenarios, such as the flooding water, the wildfire, and also the car accident. So the bottom video here is made by the National Science Foundation. So our project was selected by the National Science Foundation Science Nation video series. It shows the use of UAVs for emergency and also other scenarios. So the on-demand communication that we built can have other applications. For example, the beyond visual line of control, where the operator cannot directly see the robot, but use relayed communication to control the robot. It can also be used for multiple UAV formation and also remote infrastructure health monitoring. So the previous application shows how the CyberPhysical Systems approach can be used to equip the agents with more intelligence. And this is the last application on urban aerial mobility. This picture is from NASA that shows how our future city will look like with the UAVs, unmanned aerial vehicles. So we see that the UAVs can serve as aerial taxis to transport people across short distances. They can be used in emergency response, as my previous application shows. They can be also used for traffic surveillance, precision agriculture, cargo transport, personal assistance, sports coverage, and many other applications. So according to the market analysis, the UAV market is expected to grow $51 billion by 2015. And so there are a lot of companies that are working on this direction. This includes not only the traditional aviation companies like Boeing, helicopter company like Bell, and also IT companies like the Uber and also Amazon. So here's a brief status about the urban aerial mobility. So NASA has been taking the lead. The effort really starts from 2012, where the 6 UAV test sites were launched, including one in Corpus Christi. And in 2014, there were 4 TCL levels developed, including from the less dense areas to the very dense the urban areas. And in 2016, the FAA 107 rule was released. That is very important because it allows the non-commercial operation of UAVs. And in 2017, there was 10 IPP programs being implemented that the purpose is to show how the UAVs can be integrated into the airspace. 2019 was UTM, was a UAV traffic management pilot programs, phase 1 and 2, and 2020 is the NASA Grand Challenge. So all of these efforts have been conducted in sequence to enable the safe integration of UAVs into the airspace. So I worked on air traffic management before and developed with MITRE the flow contingency management for air traffic management. So if we look at the traditional air traffic management with the traffic management of UAVs, we see there are a lot of differences. For example, the UAVs are more uncertain. They have heterogeneous vehicle types, and also there are diverse partners and also UAV service providers we call USS. So all of these are very different from the traditional airspace governed by the commercial airlines. So to address the urban area mobility, there are fundamental research challenges along multiple directions, including on the vehicle side, like the UAS vehicle and the ground support automation, and also the airspace side, for example, the capacity and also airspace management, and also the mission planning of UAVs, contingency management, and also human systems. Human is also a very important part of this whole story. So my group has been worked on several directions under this topic. So here I show some of the results, and the first is airspace capacity. So we mentioned that the UAVs have very uncertain trajectories. So we come up with a stochastic capacity framework to measure the capacity of the airspace. So basically it says how many UAVs can safely in a confined airspace. So the stochastic framework captures the random UAV mobility and also the physical constraints, that is the sense and avoid protocols. And from the modeling framework, we come up with the node distributions, the collision probabilities, which lead to the quantified airspace capacity concept. So this allows us to design the solutions to make sure the safety of the airspace. So basically, the number of UAVs does not exceed the airspace capacity limit. So weather is very important for UAVs, especially because of their small size and sensitivity to weather. So assuming that in the future we have the weather for the small UAVs, so we need to consider how we can use such weather information to guide the UAVs. And we studied a lot on the weather for the flights and also UAVs. So for example, we considered a spatial temporal scenario data to capture the weather. And we developed the influence model-based weather framework to capture the weather. And so the data basically shows not only the temporal dependence, but also the spatial dependence as well. And we come up with an estimation solution to construct the model from the observation data. Next is the UAV traffic control. Suppose the weather information is available, we can use the database to serve kind of a playbook to guide the UAVs based upon different weather scenarios. And on the right shows the solution that we come up with that integrates the offline operations, the database query of the spatial temporal scenario data, and also the online optimization solution to quickly find the best solutions. So the next one is the UAV autonomy. We have the unknown weather. So the UAVs need to be guided despite the unknown and also uncertain weather. So for this, we come up with the reinforcement learning-based solution to learn the unknown environment. And the solution allows the UAV to go to their destinations with minimized time and also energy. They can also avoid collision into the others. So based upon the mathematical solution. So this is the end of my talk. So basically, I talked about the control background and also the automation transition to autonomy, and also use the several applications to show the smart city applications. And these works are with my collaborators, for example, including Frank Lewis in EE at UTA, and other important collaborators as well. My students and postdocs also contributed significantly to these studies, and we have established a close collaboration with the local governments and also industries on technology transfer. And I also want to thank the grant agencies that funded my research. Thank you very much. So this is the end of my talk, and I would be glad to answer questions.
Thank you, Dr. We do actually have one question that came in through the question chat, and if anybody else has some questions, feel free to post them now. It says, good afternoon, Dr. Wan. Can you elaborate on what the history of industry is? Also, thank you for devoting time to educate us about what you know and do. So what is the history of industry?
Let me try to understand the question. The history of industry in terms of education, or what is the question?
I think this goes back to, it's not elaborated in here, but I think this goes back to your slides where you had Industry 1.0 through Industry 4.0. And if you can talk about a little bit more about the history of industry in those terms, I think.
Okay, so yeah, so this was about the industrial revolutions, right? So there are technologies that mark the transitions, and currently we're in the industry 3.0, and we're going toward the industry 4.0 with the new technologies that require, for example, the autonomy. There are quite a few countries like working on this kind of initiatives. So including, for example, Germany and also Japan and also US. Yeah, I think that's my question, but I'm not sure if I have answered it.
Well, thank you. It's a good attempt at any rate. So the next question we have here is, how autonomous are these unmanned vehicles really? Like, you talked about some traffic stuff. You showed a lot of videos of UAVs flying in for disaster stuff, and they were all controlled by people. So how autonomous are these vehicles really? And kind of, is it the way that it's going to get to true autonomy, or is it always going to have a human controller aspect to it?
Yeah, thank you for your question. So currently, yes, according to the FAA rules, the operators are definitely needed. And also the line of sight operation is also needed. This is for the safety issues, because autonomous vehicles may introduce safety issues to not only the airspace, but also the facilities and people on the ground. But the direction is going toward the autonomous vehicles, autonomous aerial vehicles as well. So that imposes a lot of challenges for us to address. That is why we're working on research toward those directions. And new techniques, new autonomy solutions are needed to be able to enable a safe integration of the autonomous UAVs into the airspace. So there's still a long way to go. Consider that the autonomous ground vehicles, right, are still being developed, and the aerial vehicles introduces more challenges for sure.
Thank you. You've seen probably on the news, or we've seen on the news, where people set their Tesla to autopilot and then read a book or fall asleep or whatever. Do you see that this autonomy, or moving towards autonomous vehicles or more autonomous vehicles, can actually make that so that it's not something that's dangerous, that it's like the cars would be just on some sort of a track where they know they're programmed to stay X amount behind another car, or to stay in their lane or whatever? Or is that something that's just not, that people are going to misunderstand and continue to do incorrectly?
So the autonomous driving are definitely going to happen, right? So the so there are different levels of autonomy, right? So for the full autonomy, the vehicle basically are going to drive on their own, despite, for example, the different traffic scenarios and complicated unknown things. So that is the intelligence, that's the autonomy that we're talking about, right? This is especially challenging in mixed traffic where humans are involved, because humans do not make reasonable decisions all the time, right? So if we have kind of very controlled infrastructure support, right? So very controlled traffic environment where all autonomous vehicles are involved and there are no human drivers, this may become a little bit easier. That's also some of the cities are trying, but in mixed traffic scenarios, the vehicles are going to have the intelligence to deal with not only other autonomous vehicles, but also humans, for example, to maintain the distance, the things that you mentioned. So that's where we're working on the game theoretic approach, which can handle not only reasonable players, but also unreasonable players as well.
Very interesting. So what do you see as the next steps or the next iterations of this smart city thing and autonomy in smart cities? Is it going to be traffic? Is it going to be drone deliveries? What kind of things do you see happening in the next, say, 5 years or 10 years?
Right. So yeah, the smart city really includes a lot of components, right? So every aspect of the human life, like for example, including the finance, right? How people do studies, how people go to work, like all aspects of the society. So the UAV delivery is one component of it. So that's along the robotics side of it, right? But there are also many other things like the IoT, right? So the edge computing are involved, right? So for example, even for the mobile agents, like the vehicles and other things. Yeah. So it really covers all the aspect of our human life. It's not only the automation in industries, right? So but the things that we use, right, at home, at work. So the equipments are going to have the intelligence to make our lives easier.
Fantastic, thank you. We'll give it one last call for any other questions. And while I'm waiting, I'll go ahead and let you know that next Friday at noon, February 19th at noon, we'll have Xinbao Yu from the Civil Engineering Department. He's going to talk about geothermal de-icing systems for bridges. It's very topical since we had an ice day yesterday and we're looking at a big snowstorm coming next week. It's using geothermal energy to heat bridge decks and how he's doing that. And he's got a research station here just a few miles from campus that he's actually testing it on a full-scale bridge. So he's going to give us some information about that. I don't see any other questions, so we'll go ahead and say thank you to Dr. Yan Wan. We appreciate your time today. It was very interesting, and we look forward to seeing everybody next week or at a future one. Again, the link to all of the future and past recordings is in the chat right now. So if you want to find that, you can find that. If you missed it here in the seminar today, go to the UTA College of Engineering website at uta.edu/engineering, click on the Outreach tab and look for virtual brown bags. And with that, we're all set. Thanks very much and have a great weekend.
Thank you.